Chapter 4, Variables, Browning's Introduction to Programming with Python. Hello everyone. Today we're going to be discussing Chapter 4, Variables, from the 5th edition of Browning's Introduction to Programming with Python. Variables are something that you've used before in math, and they're certainly very appropriate in computer programming. And in actual fact, if we didn't have variables that would change over time, it would make programming a computer quite challenging, to say the least, as it was maybe in the 1940s when you had to physically rewire the computers to reprogram them, as opposed to doing it with software. So a variable is something whose value changes over time, and it could be that you set this variable one time in the program and it doesn't change for the length of the program, the actual duration of the program runs. This is referred to as a constant variable or a constant, but still it would be cleared out when the program was finally done and you could reuse that space. So data that is stayed or stored in a memory location is a variable. It has a lifespan depending on how you set it up in the program. Could be referenced by a nickname instead of the actual memory address, which would be a hexadecimal number location. So you might have a variable called tax rate, or a variable called sum, number one, first name, age. Any of those would be valid, potentially as references to a memory location that stored your variable data. A game score, character points, last names. Those are all potential things that could be variables. Obviously, there could be more. That's a short and sweet definition of a variable. But let's take a bit and look more at the history of how this came from, and more specifically, how Python handles variables, which is a little different than some other languages do. The ability to store data is a key success of a modern computer. Instructing a computer to perform a task is the job of the programming language. Python, C++, Visual Basic, Java, those would all HTML. Those are all programming languages, you could say. All right. Basically, before you had software, then the von Neumann architecture, the VNA architecture, you had to physically rewire the computer to reprogram it. Certainly that's a challenging and time, drawn out process at the very least. ENIAC from the University of Pennsylvania at the end of World War II, it had to be physically rewired to reprogram it. So, as an example, if you had to write all 20 plus million lines of code for Windows 2000, older version of Windows, but still, it's a lot of lines of code. The ones we've written before are no more than 5 to 10 lines of code. Think about 20 million. All right. What if you had to redo that every time you wanted to run it? You couldn't just save it, commit it to memory locations, things of that sort. Not good at all. If you look at some of the older computers, like I said, ENIAC and pre-ENIAC, like the ABC computer, they had switches and tubes that you used to actually program them. You did not have software, so much more difficult. And really, these were special purpose machines. They were hardwired or programmed to do one thing, and that's what they did. They weren't general purpose computers like we have now. So that's probably a big distinction you want to think about: a special purpose versus a general purpose computer. History here. Many inventions start as a solution to a problem. If you look at the punch card by Joseph Jacquard, this was a solution to a problem. Basically, they needed a way to reproduce weaving patterns on looms when they were making fabric. And so he actually came up with the idea that, hey, we could use a punch card, and the machine would actually read these cards, and it would know which thread to use to make the weaving pattern. And that was actually the software, of the weaving loom. And they actually used those cards on those machines with not a ton of changes up until the 70s, believe it or not, 1970s. It just worked so well. Vaucanson, Jacques de Vaucanson, in 1745, also known for his early robotics work, used a punch card design for programming those robots. So that's kind of interesting too. If you look at the picture of a punch card, you'll actually see how those work. And they were using those as late as the 70s at universities for student data entry. So don't think that this has gone anywhere. And you'd actually have, potentially if you were a programming student, you'd have a box full of punch cards in a specific order that you'd have to feed into the machine. And again, we're talking about, 70s, not too long ago when this was actually done. Let's see here. Charles Babbage incorporated a lot of Jacquard's work on his analytical engine. Herman Hollerith, who is someone you want to know about because his company and his tabulating machine later became IBM, used a series of punch cards with that, but actually what ended up happening was a little wire would go in through the hole or not, and if it did go through the hole, it would actually touch a cup of mercury, which is liquid metal, and that would complete the circuit. So again, we've got things that are similar to a binary machine, that on and off, and it's an electrical signal ultimately. So you might look up Herman Hollerith and his tabulating machine. Fascinating. If you get a chance to go to the Holocaust Museum in Washington, D.C., as of not too many years ago, in the late 90s, I'm dating myself here a little bit, when you first walked in, they actually had a huge wooden desk with dials on it, or that's what it kind of looked like. But actually, that wooden desk with dials on it was one of the IBM Herman Hollerith tabulating machines that the Germans had used. They'd purchased before the war when we were, friends with them, and they used those in the concentration camps. Totally fascinating. And again, they had a cup of mercury. They had the punch cards. If it could go through the hole, complete the circuit, fine, it incremented the dial to go to the next number, increment the variable. If not, stayed where it was. Some foundation concepts that you want to be familiar with as far as memory and computers. Mauchly and Eckert at the Moore School of Electronic Engineering at the University of Pennsylvania in the late 40s. They actually came up with the ENIAC computer and built that. They worked a little bit with John von Neumann, and he determined that you could make a general purpose machine that you didn't have to physically rewire, and it's von Neumann architecture, VNA architecture, which actually is silkscreened on most of the computer motherboards today. You'll see it says VNA architecture, and it basically has a concept of a shared memory technique. He wrote a paper on it, but did not include Mauchly and Eckert in the paper. When you're a university professor, it's pretty important that you have publications that you can do. And so there was a little rift between the two. They didn't really have a lot of love for each other after that. But John von Neumann is interesting because he's one of the rocket scientists that worked on the A-bomb. So he certainly was a brilliant mind on a lot of different things that he could do. The ENIAC was based on work from Dr. Vincent Atanasoff, which is creator of the ABC computer. Mauchly and Eckert talked with him, and he said, hey, I'd do this a little different if I was going to build a bigger one. And so, a lot of the stuff, it builds on previous work. It's not that someone has just come up with something off the top of their head. Let's see, you want to be familiar with probably Alan Turing, who was just recently, as of 2019, I believe, knighted by and given a pardon, some other things like that, by the British government. In World War II, he was the spearhead who came up with the Colossus computer, which helped the British and the Allies decode German Nazi messages that they'd encoded with the Enigma machine. The Enigma machine is a cipher machine that's based on the day's cipher combination, makes a different cipher code every day. And if you had the book, and you knew the day's cipher code, you'd still have to have the machine to know how it changed, the letters. A's became C's, let's say, on a certain day. But he created the Colossus computer, which is a special purpose machine that helped decode those messages. It's really fascinating because what happened as allies, we could decode all the messages they sent wirelessly, but we couldn't actually use all the information. Because if we had, the Germans would have known that we were, intercepting their communications. So we had to let some of the information go, not tell people, and lives were lost. We actually did the same thing without a computer with the Japanese. Right during the Battle of Midway, we cracked their code, and throughout the war we were able to decipher their messages. But again, couldn't let them know that we did that, so only the really good information we'd act on. Let's see here. Moving on along, we want to see John von Neumann. Again, we mentioned that he came up with the concept of a shared program technique and conditional control transfer. Shared program technique states that the actual computer hardware should be simple and not need to be hand wired with switches or vacuum tubes for each program. Okay, now they might have tubes and switches in the machine, but they were general purpose. They weren't being rewired with those. Okay, a better method would be for complex instructions to be used to control simple hardware, which would allow reprogramming to be much easier. Again, this is the cornerstone foundation and design of our modern computer that you're using right now. Conditional control transfers related to the concepts of sub-procedures in Python would be referred to as function definitions or def statements. We'll get to later on. They're reusable small chunks of code that could be used repeatedly, one time, many times as you want, one time only, and basically make the code easier to understand conceptually. And also you could reuse those code segments in other programs, which kind of leads to modular programming. Could make the code smaller potentially, could also make it easier to find errors. Conditional control transfer states that a computer code could be able to be branched based on logical statements such as if and else, repetition structures that we'll be studying in the next few chapters. Generally speaking, code libraries such as Python's rich math collection could also be considered in discussions of sub-procedures because they're just reusable chunks of code that you branch off to. And we'll look at the math library and things like that in Python as well. But suffice to say, John von Neumann did a whole lot for computer programming and computers in general, and we're still using his ideas. Now, of interest, you might look at the first commercially successful magnetic electronic variable storage or memory. It's called ferrite core memory or just core memory. And you'll see a picture there, and this is exceptionally larger in scale. If you took say an elementary school number 2 pencil, the fairly large ones, not the small yellow ones, but the bigger ones, and you drew a small dot on a piece of paper, that's about actually how big these small ferrite core magnets are, with associated very thin wires going through. This is one small segment. If you could imagine a piece of fabric with those little dots all over it, that's actually what a piece of core memory looks like, and it's about on some of the old IBM machines 1.5 to 2 feet by 2 feet square, and you'd have a series of these, which is your actual memory. Now, if you think about basic magnetism and how that works, you have your poles on your magnet. And with an electromagnet, like if you took a nail and a battery, like an iron nail, and you wrap some wire around it, you could actually make a magnet out of the nail, right? You have a north and south pole. Well, think about running that current through the nail and getting a north and a south pole, and then maybe if you provide only a little less current and the magnet doesn't work, right? That is actually the concept of how your core memory works. If you have enough power going through the wire to make magnetically charged, then the charge can go through the current. If not, it can't go through. And it's just fascinating core memory. They used it in ballistic subs, and they also had it on the space shuttle, believe it or not, in some instances, because one of the interesting things about core memory is when you turn it off, turn the computer off, it's using it, unlike a regular computer, your memory gets cleared out, machine reboots, it goes through a post-test, does all its little business. If you're using Windows 10, it takes forever to reboot, if it does a full reboot. With core memory, it stays in its last state. So whatever was in the variables, as soon as you turn it back on, they're there immediately. Well, think about a ballistic sub launching intercontinental nuclear ballistic missiles. Pretty important stuff. Needs to happen without a reboot if the computers went bad. Or think about space shuttle coming in back to orbit. It potentially, if there was a screw up, it could burn up, and the machine needs to be rebooted. Well, with core memory, you can just literally flip a switch, turn it back on, and it's back in its last state very quickly. So kind of interesting. Dr. Wang was one of the people who worked on that, but there's some others as well. How memory and variables work together. If you consider our tax program and stuff like that, you might have a variable called tax underscore rate, or subtotal, total, any number of different things like that. One of the big things that you want to note with variables are, don't start them with a numeric value, no spaces in a variable name. Make your variables kind of descriptive too. When you're giving them a name, X, Y, Z, unless you're dealing with coordinate points, on a grid, probably not the most descriptive variable name. Tax rate, we can pretty much guess what that is. It's self-documenting. Subtotal, total, first name, last name, F underscore name, L underscore name. Those kind of make sense. Give them some names that make sense. Typically, depending on the programming language, uppercase and lowercase matters. You've got a couple of options with that. You can do camel casing. With camel casing, each word in the variable name has its first letter capitalized, the rest is lowercase. Or you can do something called snake case, which you use hyphens between the individual words to make them a little easier to read. Just make it easy on yourself, though, and make it easy on the team or other people working with you. Make your variables as easy to read as possible. Now, we've got a compute your miles per gallon program. We have some comments at the top. The name of the program, date, version number. We put some extensive comments after the variables, and we've actually declared them manually. We wouldn't have to do that in a Python program normally. Other languages you might. This is just for general clarity in programming. But if you would, try out the example, compute your miles per gallon, and then when you're finished running that, resume the recording. Okay, so what you notice when you run the program, the variables change, every time you run it potentially. All right, you declared them, but again, you don't have to. Python is a strongly, or with a strongly typed language, you do have to declare the variables type and size. For example, miles per gallon is going to be a floating point value, and it is going to initially hold this value, let's say. Potentially you have to do that. With a non-strongly typed language, Python is a non-strongly typed language. VisualBasic.net can act that way. There are other languages that can act that way. Kind of a VB, you have to tell it whether it's going to be that way. By default, it is not. But with a non-strongly typed language, you give it an initial value, the variable. So we have a variable called tax underscore rate, and we give it 0.07. And then Python says, oh, they gave me a floating point value. I'm going to make it a float. Now, if we said tax underscore rate equals Sebastian the cat who helps us program, all right, it's going to make it a string, which is not what you want, because then later on in the program, you'd probably try and enter a value, and then it would try and multiply Sebastian by the value, and it wouldn't know what to do. So that is one of the drawbacks that we will learn how to address actually later on. We'll check that the user did enter what we wanted them to enter. So rest assured we'll get that worked out. But that being said, Python is a non-strongly typed language, and when you give it the initial value, it auto-types itself. All right. Now, data type and what's stored in a variable. Other languages do this as well, but you may want to determine actually what Python thought you gave it. What kind of value did you give it? You think you gave it something, but maybe it auto-typed it to something else. So we have the type command. Type command is very handy, simple to use. It's just type and then the variable in question that you want to look at. If you want to try the example there of foo is equal to 1.2, and then we're doing this from an interactive prompt. You could do it from script mode, but you would need to have print in front of it to actually see the results. So it would be print space type foo. But try that example out, and then try it with some of the other examples that are there. Is 1.111 and some of the other things. And let's just see what Python thinks these variables are. Hit play when you're done. Okay. So the first output's a float, the second an int, and the last type, str for string, tries to pick the best match that it can and assign it to that variable. All right. Now, let's see here. We're going to find the variable's type with the Fahrenheit and Celsius program. We're converting from Fahrenheit to Celsius. Try that example out and try out print space type Fahrenheit, and it'll actually tell you what data type it thinks it is. Hit play when you're completed. All right. And then if you rerun the program with the challenge, but you give it an integer value, all right, it's probably going to give you an integer, all right? And the reason is you were doing integer arithmetic and there was no point for it to, promote it to a higher value. That's an interesting thought. What's going to end up happening here is if you give it a more precise value and it tries to use less precise values to do some math operations on the end result, it's going to promote all the other ones to more precise values. What in the world am I talking about? For example, in that last program, if you'd given it a 96, it would have subtracted 32 from that, multiplied that by 5 divided by 9. All right, those are all integer values. Would have done integer arithmetic on it. But if any of those had been promoted to something more precise, if you typed in 96.0, if you'd had 32.0, or if you want to throw it off slightly, 32.1, whatever, they would all be promoted to more precise values. So the next option up, more on variables. Answer the question above as Python tries to pick the best data type for a variable. All right. Now, if you look at the list on the next page, you'll see some of the variable types that Python actually stores. Some of these are a little different than what you can do in other languages. But again, integer, float, booleans, longs. We also have octal numbers, base 8, hexadecimal, base 16, character strings, and actually we'll see that individual characters and strings all behave the same way. So, if you would, let us try out the octal number example at on the next page, and you'll notice that the integer values are preceded by a 0. That is somewhat common with other languages. If you don't do that, it's going to do it as a base 10 number instead of base 8. Try that out, and we will move on to the next example. Hit play when you are completed. So now that we know how Python types variables, we want to find out how the variables are stored in memory. All right. Python variables are actually referred to as immutable or unchangeable. What? Well, we just changed them. That's not true. Well, actually, it is. The way Python handles storage of variables is when you change a variable, say you have one called tax rate and you make it 0.08. All right, and then you change it in the program later on to 0.07. This is while the program's running. It actually creates a brand new variable with the exact same name, masks the other one, and hides it away. And so there's actually two memory locations with the exact same name, but you're using the most recent one. And if you switch it back to the original value, it goes back to that original memory address. It doesn't recreate another one. So it's a little bit of efficiency there in that respect. So if you try the example out with the ID function, which will tell you where numerically a variable is stored in that actual microprocessor, in RAM, all right, you'll see that we create a variable called x, which is equal to 10, and we run the ID function on it. This is from the interactive prompt. Gives you a memory address. Yours will be different because it depends on what memory is being used that the program will assign it to. Then you change it. Say we change it to x plus 1, so it's going to be 11. It's going to store it in a different location. You change it back to 10, note that it's going to be the original location. Try that out, and then we will resume with the next part of the text. Okay, so that was pretty interesting. So the ID function, it's built in, and basically it returns the identity of an object or where it is in memory. All right. So now let us look. Constants in Python. Technically, since it's a non-strongly typed language, Python really doesn't handle constants, but you can work around that. All right. So constants or constant variables, variables that don't change over the lifetime of the program, or if they do, we want to know about it so we can handle it appropriately. There are a couple of examples in the text. We won't use the example from Alex Martelli. It's a little more advanced. You might try it later on. I mean, you're welcome to, but I think an easier way based on what we've been talking about is the example you see, Constance example number 2 there by J.B. Browning. And what we're going to do, if you think about this, is we're actually going to find out where in memory the variable we created is. So we're going to find out what the numeric value is. It is stored at location 33619, let's say. All right. And then before we go use the variable, we're going to check and see where it is in memory. If it's not at the same memory location, then guess what? Your variable changed. It's not a constant. Then we could handle things, differently. All right. If it is at the same location, fine, dandy. It's a constant. It hasn't changed. Let's use it like it is. So that is in fact what this example does that you're going to try out. You'll determine what tax is. We have used all capital letters for our variable as opposed to camel casing or snake case. Typically, convention with programming languages, all uppercase for a variable, it's a constant. If it's lowercase or a mixture, then it is a true variable. It should change over time. All right, so we have tax then in all capital letters. That's a good convention you probably want to stick with no matter what language you're using, just for consistency's sake. But try that out, and then we'll see how it works. Hit play when you are done. Okay. So in this chapter, we've learned a whole lot, a little bit of history, about John von Neumann and V&A architecture, strongly typed language where you have to declare the variable versus non-strongly typed like Python, where it declares the variable's type automatically based on what you give it. We learned a little bit about punch cards. One of the last interesting things about punch cards is, if you're familiar with software piracy, stealing code, one of the very first instances of software piracy was when competing loom fabric manufacturers would go and steal punch cards from the competing factory so they could get the patterns for their cloth. And that is the actual first documented case of software piracy, 1800s. Kind of interesting. Try the activities at the end of the chapter to test your knowledge and reinforce what you learned in the chapter, and we will look forward to talking to you on Chapter 5. Have a nice day.